I have a college algebra final exam question about compound annual interest rates. So we are investing at a 5% annual interest rate compounded continuously. Order the following from 1, taking the least amount of time, to 4, taking the most amount of time. So we have growing 1 to $2, 400 to 900, 1 to 3, and 300 to 800. So how do you go about doing this problem? So for one, let's just review briefly about compound interest rates. So for compound interest, the amount accrued is going to be obtained by the following formula. So P, the principal, the starting amount, times 1 plus R over N, and that factors to the NT power. So N is the number of compounding periods per year. So N times T is the total number of compounding periods. And at each compounding period, you take the principal and you multiply it by this factor, 1 plus R over N. So the fraction that you add on to 1 is going to be the annual interest rate R divided by the number of compounding periods per year. So for example, if you have an annual interest rate of 10% and you compound quarterly, at each quarter you will multiply the principal, or the current amount, by 1 plus R over N, which would be 1.025. Okay, so compounding continuously means that we take N to infinity, so we compound at every moment. You can do this. You can take N going to infinity, and you'll get P. So let me write this quick. You'll get P times e to the RT. E here is Euler's number, about 2.718. The reasoning for this, I'll just write down quickly, is you can rewrite this expression in the following way. And then you can put parentheses like this. So certainly this term here is going to approach E as N goes to infinity. And that's because R is a fixed positive number, so N over R also approaches infinity. And there we go. Now, I suppose certainly you can say that every one note. Okay, so you can slip parentheses around here to see that the non-continuous case is an exponential function, and you can also do it over here. Right, an exponential function for me would be something of the following form, where f of t is a times b to the t. A is non-zero and b is a base. Okay, so a base means that you are either greater than 1 or strictly between 0 and 1. In this case, we call that exponential growth, and in the latter case, we call it exponential decay. It turns out for any exponential function, there is a notion of k-tupling time. Which we'll call tk. Here, k is a positive number. Sorry, let me rewrite tupling here. So this is defined by setting f of t plus tk equal to k times f of t. But note that if you plug this in, you will get a b to the t plus tk equals k times a b to the t. This is really just a b to the t b to the tk equals k a b to the t. And we have some cancellations, so we end up with b to the t capital Tk equals k, which of course if you solve for capital Tk, it's just log base b of k. And then you can get several other nice consequences of this. Let's say if you have alpha and beta positive, then T alpha beta is just log base B of alpha beta. Whoops. Which is log base B of alpha plus log base B of beta, which is just T alpha plus T beta. So if you so more concretely, for example, if you have a certain amount A that you start with in your investment and you wait T2 time, remember in this process here, we canceled A, little a, which was the initial amount of our exponential function, and we canceled b to the t. That doesn't get rid of b, but it gets rid of little t. So what that ultimately does is it says that it doesn't depend on the initial amount. So at any point in our exponential function, if we wait tk units of time from some starting time little t, we will have multiplied the amount by k, where tk is this log base b of k. So in our picture, if you wait t2 time, you will have doubled, so you'll get 2a in your amount in your investment. If you wait an additional t3 units, you will have tripled that amount 2a to 6a. But ultimately, we just waited t6 units of time. So t6 is t2 plus t3, which is sort of an example of this fact we just demonstrated above, which could be seen as a visualization of the log product rule, which is basically just used here. All right, so let's clear this out here if I can. Clear some of this out. Okay, so let's finish up the problem. There's one other observation we need, is that if 0 is less than alpha less than beta, and b is greater than 1, which is the case for our setup, because the base here would be e to the r, which is e to the 0.05, which, since e is greater than 1, is e to the 0.05 is greater than 1 as well. Okay, so in these assumptions, then T alpha, which is log base B of alpha, is less than log base B of beta. That's because log base B is an increasing function since B is greater than 1. And so we have this. So what this means is that in our case, we could do this in the following problem. We could say, okay, what is the time it takes to grow, let's say, $1 to $2? Well, you just write down everything in our equation. Like the amount now is 2 equals p e to the rt, and solve for t. So if you solve for t, this one is pretty easy. It's just going to be a natural log of 2 divided by 0.05. And you could do that for each of these 4 cases. The point is, after all the theory we've developed, that actually is unnecessary completely. Instead, all we have to do is look at the time it must take for each one. Each of these investments is with the same function, same exponential function. So to grow $1 to $2, this takes T2 time. To grow $400 to $900, well, it's T 900 over 400. That's the multiplier to get 400 to 900. That is 9/4, which is 2.25. 1 to 3, this will take T3 time. 300 to 800, this will take T 2.6 repeating time, or T sub 8/3. So certainly we, at this point, know that T2 is less than t 2.25 is less than t, t sub 2.6 repeating is less than t3, and therefore we can answer the question. We have to order them from 1 to 4. 4 is the least amount of time to 4 the most amount of time, so we're basically writing first through fourth. So first place is investment 1, second place is investment 2, third place is investment 4, and fourth place is investment 3. All right, thank you very much.